So as promised, we will talk about heaps in this video, and in particular we want to talk about the binary max heap. And heaps, as we said previously, help us do a lot of things very elegantly. It's a very clever data structure, and what we'll talk about later is how to use heaps to implement a fast priority queue. So first, like we said, we are talking about binary max heaps. Max heaps. So this binary part, what do we know that's binary? Well, we know about binary trees, and we're not going to talk about binary search trees. This is binary trees, so don't get it confused. It's not a binary search tree, right? It is just a binary tree with the property that any node has at most 2 children, right? So that's what a binary tree is. But it's not just any binary tree. The binary trees we're talking about will be said to be nearly complete, and in such a way that we have some kind of binary tree, but nearly complete. What this means is that anytime we have, let's say our binary tree has p levels, it'll have p minus 1 filled levels. So all p minus 1 levels will be complete, and the pth level, the last level, will be almost complete, or it may or may not be complete. It certainly could be. It certainly could be the case that it has all these nodes and it's a complete level. So that's possible. Or if it's not complete, then it has to be complete from left to right. So this is valid, this is valid, this is valid, this is valid. But what's not valid is doing something like this, or something like that, or something like that. That's not valid, because in that case, we're not going from left to right. We're just randomly inserting wherever we want, and that's not allowed. We want to go left to right. So this is the direction we want to go, and in the last level, we want to fill our binary trees nodes from left to right in that last level. So okay, so now we know how we're going to store data. We're going to store it as a binary tree, as nodes in the binary tree, and it'll be filled in the bottom level from left to right, which is good to know. But how is that any different from binary tree? Well, this binary tree is going to be special in that it'll have a max heap property. So we're going to have a max heap property. So this max heap property is going to say something about how many children, or rather, how the priority of a parent's child is relative to the parent. So what this max heap property says is that if you have any parent, then it must have a priority higher than any of its children, right? So its children must have a priority that's less than the parent, right? So priority of the parent is always greater than or equal to the priority of its left child, and also greater than or equal to the priority of its right child, right? So this is the max heap property. And if we fulfill this max heap property for every node, then we can say, yes, indeed, this is a binary max heap, or simply a max heap, right? So this is the only kind of heap we're going to be talking about for our purposes, max heap. So, okay, so now that we know what this max heap kind of is, how do we sort of store it? So for now, it's still something like an abstract data type to us, but it does have an implementation, and in fact, this is supposed to be a data structure which implements other, ADTs such as priority queues and things. So how do we implement this heap, right? So we can use an array or a list, or we'll just call it a simple array, right? So we'll just use a simple array to store our data in this max heap. So say we want to store some kind of max heap that looks something like this. So there's X, Y, Z, and this Y has two children, A and B. So we want to store this max heap in the array, and it's not too tricky, as you'll see. So notice that each level has at most 2 to the power of that level minus 1 element. So this is 2 to the power 0 in the first level, 2 to the power 1 in the second, 2 to the power 2, and so on for every other level, right? So we can use this, and remember that nearly complete enforces this rule where our last level has its children being filled in from left to right. So from left to right, we fill in our children. So the next one would be here, the next one would be there. So from left to right, it's very deterministic. We kind of know the structure of this. So we can in fact store this simply as a sort of a level order traversal of this binary tree, right? We go level by level from left to right, level by level, level by level, and we can just do a level order traversal of this binary tree, and we store all our elements in that way. So this would just be something like X, Y, Z, A, B for what we see here below, right? Using just a common double order traversal, that's what we get. So, okay, that's cool, but now this looks so much different than a picture like this. With a picture like this, we see, okay, X, well, the left subchild of X is Y, the right subchild is Z, and if you take a look at something like B, this B here, well, the parent of B is Y, so, okay, so that's pretty intuitive stuff. But how can we say, oh, what's the parent or what's the child or what's the left or right child of any of these elements here in the array? Well, that's also not too difficult to do. So let's see how to do that, right? So here let's see. First of all, let's make this a rule. We're going to have the convention that indexing starts at 1. So I equals 1 here. This X element is at index 1. And in fact, that is going to be the maximum element because it is the root, right? Maximum priority element because it's the root. So, okay, indexing starts at 1. That's what we know. How does that help us? Well, now we can sort of use the fact that indices start at 1 to find any left child or right child of any element at a given index using this rule. So the left child of the element at index I is going to be found at index 2i. The right child, similarly, the right child of the element at index I is going to be found at index 2i plus 1. And the parent of the element at index I can be found at the floor of I over 2. So the index, which is the floor of I over 2, is where we can find the parent of I, right? So floor, if you haven't seen it before, floor Z just means that we take the integer part of Z, or rather we round it down to the nearest integer. So that's just what flooring means. We just take the integer part of whatever it is, right? So heaps are used for a lot of different things, and as a computer scientist, it's very important that we know a lot of these applications. In fact, if we look at the memory model in systems programming, we know how heaps are used for dynamic memory allocation, and they have all these bunch of uses. We're talking about max heaps though, so we're going to use max heaps to implement priority queues. So for a priority queue, we have these four operations we defined, right? And in case you don't remember what those are and what they do, you can watch my previous video on queues. But okay, so we have these four operations, so we'll just go through them one by one. So for priority queue, we have a bunch of operations, and the first one, the max method, right? So we have this method called max, and what max does is we just get returned back the max priority item in the priority queue. So we know that the maximum priority element is precisely the root element in a max heap. So if we have, let's say, a array, the array representation of this heap, then that's just going to be the heap array at 1. Remember, our indexing begins at 1, so that's why it's heap array at 1 rather than heap array at 0. And this is just always getting the first element, so it's always going to be theta of 1. It's constant time, right? So that's pretty simple. That's very simple. No matter what kind of array we have, what kind of heap we have, we just get the first element, and that's the max. Okay, that's good enough. Now, what about insert? We have this other method called insert. And for priority queues, how do we insert stuff? Well, here is where it gets slightly tricky. It's not too bad, but slightly trickier than something straightforward, which we did in Max. So for this, what we do is we first we'll have two steps. The first thing we'll do is we're going to add the node to the next available spot in the heap, or in the array representation, this would just be like appending. So say we have a bunch of stuff, and we want to add this next, insert this x, well, we add it to the next available slot, or rather to the end of the heap array. So we just append to the heap array, right? We append to the heap array, and in a heap, say we have a heap that looks something like this, right? So this is our current heap. Then we're going to insert it over here. This is where the insert will take place, right? This is where we insert the element x. So that's what we'll do first, right? And notice, if you're sharp, then you would have probably noticed by now that this does not meet the max heap property. Sure, it's a binary tree and it's nearly complete, but it does not retain the max heap property. So what do we do? Well, this is where step 2 comes in, right? We'll move all this stuff up. Step 2, we do what's called bubbling up. We bubble up. Right? And what bubbling up means is, and we don't necessarily have to do bubbling up if the thing we inserted is low priority or low enough that it retains the max heap property. But say it breaks the max heap property, then we would need to bubble up. And what bubbling up involves is we swap the new node we just added, so that node X we just added, we swap that new node with its parent if the parent is less than the new node. So if the priority of the parent is less than, strictly less than, because it's allowed to be equal to, in which case it retains the max heap property. So if the priority of the parent is strictly less than the priority of the new node, then we do bubble up, or which means we swap the new node with the parent, right? So maybe in the heap array, if we look at the heap array example, that might look like heap array at the parent. So the parent, where the parent was before, let's say floor I over 2. Remember, this is where we get the parent's index using floor I over 2, where I is the index of the child we're interested in. And in our case, the new node's index is going to be I. So new node is going to be index I. So this is just some Python syntax for swapping. I'm just going to fill in. So HA at floor I over 2, comma HA at I is going to become the heap array at I, comma heap array at floor I over 2, right? So this is going to swap the position of the parent and the new element if the parent is of a lower priority than the new element. Okay, so we have that out of the way. Are we done? Well, remember, we bubbled up here for a reason, and that was to make sure that the max heap property was retained. So if the max heap property is okay now, then in fact we're done. But if it's not, then once again we have to bubble up the new element to the next parent, right? So what would have been originally its grandparent or something, and then its great grandparent, and so on until it either becomes the root or somehow starts to retain or stops and retains its max heap property, which means that its parent is greater or equal in priority than itself. So yeah, so we repeat until we have a max heap. We satisfy, you guys can't even see that, so repeat until max heap property is satisfied. Property satisfied. Okay, so we'd keep bubbling up until we find that the max heap property has been satisfied. And remember, every time we bubbled up, right, we were performing one swap. And how many times at most do we perform the swap? Well, the number of levels there are is the maximum number of times we would have had to bubble up. So that's log n. And in fact, it's precisely because of this reason that we have a running time in theta of log n for this operation insert, right? So for insert we have theta of log n. Okay, so that's two priority queue operations we talked about so far. What about the other two? So the other two turns out are use sort of the same concepts as in inserting, and in particular they both make use of bubbling up or bubbling down or something. So let's talk about extract max first. Extract max. So if we want to perform extract max on our priority queue, and we've implemented our priority queue using a heap, which is of course the right thing to do, that's what you should do, then how do we do this? Well, we know the max element is the root element, right? So in any heap, this root element is the max, and it necessarily has to be the max because of the max heap property, right? So the root is the max, we know. So what do? Well, we just replace the last element. So let's say we had a heap like this, and okay, so this was our heap, and all these levels were filled except for this last one. This last level was partially filled, and there was an empty spot here. So what we would do is take this last element, right? So take this last element, this one right here, and we put it where the root is. So we make this thing the root, and so it looks like this now. This thing that was here is now this thing, the new root, and now we have a heap that looks like this. But where did the old max go? The thing that was the max? Well, we just store it on the side here. So this was the max, the old max. We just kind of store it here on the side. We don't need to use it for now, but we'll return it once we're done all our work. And in fact, there is work to be done. We're not done after we do this, because we just, I mean, look what we did. We took the last element thing and we made it this new max, or the new root, which, I mean, does it even deserve to be the max? It could be the case that it is equal to all these nodes are equal, and you know, this is also equal to what the max was previously, and it could have been, but there's a good chance that that's not the case. So if that's not the case, then we'll have to do something called bubbling down, right? So okay, so before we do it, I just want to quickly mention that the heap array at 1 is what we store, right? This was heap array at 1, and we popped it and we stored it, but at the same time we had to take a heap array at the last index. So heap array at n, where n is the last index, and make that look like an H. So heap array at the last index and put it at heap array at 1, right? So okay, so that's what we did. So after we've done that and we've stored this max element on the side, or which was previously the heap array at index 1, because remember our indexing begins at 1, not at 0. Now that we've done that, we'll have to potentially bubble down. And assuming it is the case that we now have broken the max-heap property, we'll have to bubble down. So what do we do to bubble down? Well, we take this new root element. Now we compare its value. So we have this new root element, and we compare its value, the value of this root element, with its children. right? So this left child and its right child, and we take the largest child and we bubble down. So in other words, we swap its largest child. Let's say this was the largest child. So let's say this right child was the larger child. Now that right child is swapped with the root element, and this root element comes down. And now let's say there were even large, right? So there were even larger children of this thing, and they were smaller than this, you know, this new node. Then we would have to bubble down again and again and again, all the way until this thing is in the right place and the max heap property is retained. And we kind of know how bubble down works, right? Because it's pretty much identical to bubbling up, except we're comparing now with the children. And we know how to find the children because we know how to find the parent. We just kind of reverse the process and we find the children. So yeah, that's how we bubble down. Or sorry, not reverse the process, but we know how to find the children because the left child, we said before, the left child of the element of index I is at 2i, and the right child is at 2i plus 1. So that's why we know how to find the children. So yeah, that is pretty much what we need to know for extract max. So now that we know that, how is the time complexity on extract max? Well, this is also going to be theta of log n for pretty much the same reason as we argued in the insert operation, because we have log n levels, and bubbling is basically doing log n swaps for that reason. So, okay, so extract max is log n. Now we are left with the this last method we need to implement, which is increase priority. So increase priority. And how we're going to implement this increase priority is, well, let's say we are specified an element x, and we're given that we want to increase the priority of x to k. So what do? Well, we take x and we say that x dot priority equals k. Basically as simple as that, right? It doesn't have to be anything more complex than something like this. We just assign the value k to x's priority. So now let's say we had some kind of heap like this where element x was over here, right? So now element x has this new priority k. So now element x has priority k. So because it has priority k, there's a chance that we might have to either bubble up like we did in insert or bubble down like we did in extract max. So depending on whether the priority is greater than its parents or maybe less than its children, it'll either have to bubble up or bubble down. But we know how to do that. We just swap all the way up or all the way down, and that's how we get to where we want to be with bubbling up and down. So it's not too hard. We've seen it before, and I guess we have an intuition now about how to do it. So that's increased priority. And once again, the runtime is going to be logarithmic, right? We're bubbling, and that means we'll have a logarithmic runtime again. Theta log n. And once again, it's precisely because we have log n levels and we're bubbling up and down, therefore log n times, that we're going to see that we have log n as the log n as the runtime. So okay, all right. So now we are done talking about these priority queue operations. So we saw that priority queue operations. We saw that the priority queue operations were all either constant time or logarithmic time, which is a huge improvement compared to sort of some other implementations which might have linear time for even a few. And we want, as much as possible, we want to have logarithmic or constant time, because that takes almost no time compared to linear time, which is a huge improvement from linear to logarithmic, right? If you can make something that's logarithmic to become or sorry, something that was linear previously, and you can make that logarithmic, that is a huge performance gain. And so that is why we opt to use these heaps instead of something more naive such as linked lists when implementing priority queues. Okay, anyway, one last thing we want to talk about is Heapsort. 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 So Heapsort is a sorting algorithm, and what Heapsort does is, so say we have some list. It has elements, and we want to sort this list. What do we do to sort that list? Well, we can use Heapsort to sort that list, right? So we can either sort it, reverse sort it, which is what Heapsort will initially give us, or we can sort it from least to greatest. And that just takes pretty much a linear time operation to sort it that way, but we'll see exactly what Heapsort does. Heapsort, first, it builds a max heap. So you have this array, we want to build a max heap from this array, right? So we want to build a max heap from this array. So what do we do? Well, in fact, what we'll do is we'll build a max heap in place. In place, we'll build a max heap by doing something that takes O of n time. So building the max heap takes O of n time. It takes linear time, because what are we doing? Well, we have some kind of, here, let me actually write what we're doing. Build max heap. Right, so we have some kind of heap representation of this array, right? We have a heap representation of this array, which is not necessarily retaining the max heap property, but that's the only thing we need to worry about. Just how do we satisfy that max heap property? And if we can satisfy that max heap property in this array, then we are done. This is in fact a max heap. So basically what we're going to do is we're going to look at this last level. We'll say, okay, that by default, for each subarray here, or subtree here, or subheap, I guess we can say, it already satisfies by default the max heap property, because it's got no parents, no children, or rather it has no children, so its subtree already has the max heap property satisfied. Now we look over here. Now do we satisfy the max heap property for this subtree? Well, it could be that maybe we wanted to swap this thing from here to here, bubble it up. bubble up this thing from here to here, and now they're swapped, right? They're swapped, and now this thing and this thing also satisfy the max-heap property. So now we have that this and this both satisfy the max-heap property. So are we done? Well, no, because does this now satisfy the max-heap property? Well, we check the children and compare with the parent, check the children and compare with the parent, and let's say we swap this thing with this thing, right? So now this thing goes down here, and this thing bubbles up here, and now the whole tree satisfies the max heap property because we bubbled up and bubbled up all the way until we reached the max, right? So we bubbled up and bubbled down all the way until we reached the maximum element being in the maximum spot, and the other elements, being in their respective spots. So yeah, now basically all we did was we did something that bubbled up and bubbled down until we had the max heap property satisfied, and now we've built the max heap, and it turns out this is in fact O of n rather than O of n log n, because well, there's some computation that goes in there, and you have to solve a bit of a summation and sort of use some clever tricks to solve that. And basically, my point is we can argue why it's O of n, and I won't um, I won't go into the proof for that, but if you want that proof, you can certainly find it in the lecture notes by David Liu, or rather the lecture slides by Dan Zingaro. So the proof is there if you want it. So, but here, just take my word for it. It's O of n, and now we've built a max heap, right? So what's step 2? Now we have a max heap. So what is step 2? Well, we know that the extract max function is in theta of log n time. So we call extract max n times. So we call extract max n times. So now we have, each time we called it, we got the maximum element. So now we have this array of, max, second max, or rather the second largest, all the way down to the smallest, if we were storing all these extracted elements within an array, right? So now we have the max all the way down to the smallest element, because we called extract max n times, and at each time we had log n runtime. So this is going to be theta of n log n time, because again we built the max heap in linear time, and we have n log n time to do this extract max stuff. Overall, it's going to be theta of n log n for this heap sort. So, like we said, heap sort is going to be theta of n log n for the reason we just mentioned. Okay, so that's basically all we wanted to talk about with heaps. We see that heaps have a bunch of applications in computer science, so they are very useful data structure to remember. And we just talked about a max heap, but there are several different kinds of heaps. And if you're interested, you can always do some research on your own, and hopefully this helps introduce what maybe a particular implementation of a heap and its application to priority queues can be. So thanks for watching.